Today we talk about bright amplification, and we go other session every 2 weeks. So please, Derk and Dave, show us the magic.
Okay, so let's jump into presentation mode. Right, and I'm starting. I'm going to hand over to give us the gizmo. Okay, so this is a presentation. This is actually partly a rerun of the presentation we did 2 months ago. We've made some significant improvements to the presentation. We've also got some very positive feedback from one particular dev team. There's a few places where we've actually implemented Fillfactor, a few more places we've implemented Fillfactor in the last couple of months since we presented to the whole company at the architectural review a couple of months ago. And then one team came back to us with some really good feedback, and we're going to talk more about that later on. So we're starting with this, which is, is this working? Sure. Maybe I can just do it with the keyboard. Okay, so we're starting with the Fillfactor and Postgres' dark corners. So,
First station is just saying.
Where is it? Yeah, your presentation is hanging. Okay, now it's going. Okay, so sorry about this minor glitch. Right amplification. So this was a quote or a topic which was discussed by Bruce Mongeman, one of the Postgres core team at the Postgres Build conference last December. He was talking about all the various challenges for Postgres as a open source project. On the technical side, he highlighted right amplification as one of the big ones. There is a project called Z-Heap, which could in effect in the future have a different storage engine which gets around this problem, but that's certainly several years away from being sort of ready. At least it's a year or two. I mean, you can run it in a Docker container, but there's not that much progress with that project at the moment. I mean, it's definitely something very exciting. So what can we do to avoid right amplification via Fillfactor now? And this presentation is in 2 parts. I'm doing a very short introduction, and then Derk's going to jump into the technical details about why random amplification happens, what hot updates are, and how to some of the constraints about when and where Postgres will use hot updates. And then I'm going to start looking at some of the metrics we're using to gather this and to identify which tables and which operations we need to tune, which gets quite complicated. So let's move this forward. Okay, so this is the last slide before I hand over to Derk. So in 2016, Uber decided to move away from Postgres, and they wrote a technical blog post. Why? It caused an awful lot of noise on the internet. I'm not going to go into all that, but it's important to understand for right amplification that this is something which is specifically around heavy update workloads. So one of the comments on the internet flame war was that Instagram are okay and they have a huge volume of data, which is probably true. I don't know very much about Instagram, but I would imagine they're doing a vast number of inserts of particularly pictures and text. And if you have a pure insert workload or a 99.99% insert workload, Postgres storage engine works very nicely with the default settings. The problem happens for tables have a relatively low number of inserts and a very high number of updates. And we'll come on to how we're tracking those tables and how we can identify those later on. But I just want you to have in mind that this is something around heavy update workloads. And with that short introduction, I'm going to hand over to Derk, who's going to talk a little bit more about the technical ins and outs of what's going on at the block level. Okay.
All right, thanks. Yeah, why do we have right amplification, and what is it actually mean? And to explain it, we have to go through some technical stuff, but I'll try to explain it as easy as I can. Let's look at the page. Postgres stores all information in pages. So every page starts with a page header and a page footer. As soon as we start adding information, we have a line pointer at the top of the page, and this line pointer points to the actual row of data, and we start writing the rows at the bottom of every page. if we have an index, this index points to the line pointer, and the line pointer points to the row itself. Now, let's see what happens if we update a row. We start with the initial version of a row, and when we have new information, we don't update the existing row, but we actually create a second row with all the new information. Then we add the line pointer to this new row. And of course, we also have to update all of our indexes. Otherwise, the index is not able to locate this new row. Then if we hit this page again with a write operation, so that means an insert, a delete, or an update, we trigger the single page cleanup. And the single page cleanup is cleaning up a single page. So what can we clean up on this single page? Well, we have an old row and nobody's using this old row anymore. So you can just remove this old row. Now we end up with a line pointer which points to nothing. So we have to mark this line pointer as being dead. Note here that the index is still pointing to a line pointer, but the line pointer itself is no longer pointing to any data. So this line pointer is dead. A single page cleanup can not clean up anything outside of the page. So we can't clean up the index and we cannot update the free space map. After a while, we have the vacuum process, and vacuum is cleaning up all the other stuff. So the vacuum operation can actually clean up the index. Now nothing is pointing to the dead line pointer anymore, so we can mark the line pointer as being unused. Nobody needs it anymore, nobody's pointing to it. And we can also update the free space map. So now all the processes within the cluster can see there's a vacancy on this page between row version 2 and the end of this page. Now let's look at a hot update. We start with the same initial situation. So we still have an index, we have a line pointer, and we have an existing version of this row. And now we update this row with a new version. So again, we create a new version of this row within the same page. And now we again add a line pointer, but besides the line pointer from the line pointer at the top of the page to the row, we also add a line pointer between the row versions. And important to mention here is the index itself is not updated. So there's no new index leaf and we don't need to update existing indexes. Now when the single page cleanup is triggered, then we again can clean up the old version of the row and we create a line pointer redirection. So if you use the index to access this row on this page, the index points to the first line pointer, which redirects you to another line pointer, and that line pointer redirects you to the data itself. Very important to see here is there's no moment in time where we have a dead line pointer. The dead line pointer is never marked as dead. Now we can update this row again. We create a third version of this row. We add the line pointers and we can clean it up again. What we end up with is a page with only the final version of this row, and there is a long redirection between the first and the last line pointer. So we create a chain of line pointers where all the line pointers in the middle can be unused, but we always use the first line pointer because we need it because our index is pointing to this very first line pointer, and we need the final line pointer because that's the line pointer pointing to the actual data on the page. So with a hot update, we are only updating a single page. We don't update indexes and we don't update multiple pages. Everything happens within this single page. And that's if it's not. Hot updates or the heap-only tuple updates are very efficient just because they are updating only a single page. They create this chain of rows without the need to update indexes. And the updating indexes is the actual part where write amplification takes place. Write amplification is the process where if you update a single row, you have to update all of the indexes. And that can count up very quickly. Let's do a little calculation. Let's say I have a table, and this table has 10 indexes. If I update this table 1,000,000 times, I have to update the 10 indexes also 1,000,000 times. So the difference between ordinary updates and hot updates in this case is already 85 gigabytes of ball. And that's a lot of data to write. And there are some additional benefits of hot updates. Since hot updates don't generate dead rows, we end up with very little dead rows. And when you have a small amount of dead rows, the vacuum process is also much faster. Since there are no dead rows, the indexes are not pointing to this dead row, so the index reads are much more efficient when you do hot updates. There are simple, less pointers to read from. So this is a lot of beneficial stuff for a hot update over an ordinary update. Well, if it's so much more efficient to do hot updates, well, let's stop doing the ordinary updates. Well, that's fine. Let's look at a very simple table. We have a table, DBAs, and it contains your two favorite DBAs, me and Dave. And we create an index on our age. So I'm 27, Dave is 28, he's a year older than I am. And we do an update on this table. So we update my surname. So what do? Well, we create a new version of this row. We create a line pointer. And after a while, we clean up. And everything works like a charm. So we can do a hot update and everything still works. Now, let's create a second index on this table. So besides the index on the age, we also create an index on surname. And now we repeat this process, and let's pretend it's a hot update. So we add the same amount of information, we add line pointer redirection, and now we search for a DBA with surname Van Veen. So we know we have an index on it, so let's use this index. And this index points us to the first line pointer. Then there's a redirection to the third line pointer. And finally, we end up with a row. But this row actually has a different surname than we were looking for in the index. So if we use a hot update for an indexed column, then we start using the index on an invalid way. So this means we can only use hot updates when we are updating non-indexed columns. So this is a very important part of hot updates, or it's a very important limitation when you can do hot updates. The moment you add a single index on an updated column, you lose the possibility to do a hot update. So if you already have 9 indexes on a table and you add a 10th index to this table, and this 10th index contains a column you are frequently updating. Now, instead of a hot update where you only update a single page, you have to update 2 pages and all of the indexes. So you actually multiply the amount of work you have to do by factor 12. So that's what we are trying to prevent. So these are the 2 boundary conditions for hot updates. You need to update only non-indexed columns, and we need a space within a single page to accommodate the hot update. The first boundary condition is not something we can control. Of course, we can drop indexes, but these indexes are probably there for a good reason. But we can influence the space within a page to accommodate hot updates. How do we do it? Well, we can change the fill factor for a page. Well, very short, what is the fill factor? The default fill factor for Postgres tables is 100%. So we start with a completely empty page, and then we start writing to this page, and this page slowly fills up until the page is completely full. And, well, we can't write additional information to this page, so what do? Well, we just start a new page. And of course, we have some index, and this index is pointing to some line pointers on this page. Now let's change the fill factor for a page for table to 80%. Now what happens? We still start writing to this page. So until we cross the 80% threshold, and at this moment in time, we start a new page to write new rows to. The 20% on this page we leave available to accommodate further updates. How do the updates look like on a 100% filled page? Well, if we want to update a row on this page, there's no space available to accommodate this new version of the row. So first thing we need to do is create a second page. On this new page, we can write the new information. Now we have to update all the indexes to point to this new page. And finally, we can do the cleanup. So when you now look at the very first page, there's one space available for one hot update on the first page. So even when you have a 100% fill factor on your table, you can still do hot updates because now we moved one row from the first page to the second page. So there's one vacancy on the first page. Of course, we have to mark the line pointer as being that on the first page. And if we have a table with 10 indexes, we write to at least 12 pages in this case. Now let's do an update on the 80% filled page. Well, we can actually write the new version of the row to this page. So there's no need to create a second page. Now we have to update all the indexes because apparently we are updating an indexed column. So we remove the old row and we mark the line pointer as that again. And if we save creating a new page, but we are still writing to one page and all of the indexes. So we write for one update, we have to write to 11 pages. This is the right amplification. And we end up with an index pointing to a dead row. So in this case, we actually have dead rows for this table. Now let's do a hot update for this table. We again add the row to the same page because we have the available space to accommodate this. And finally, we remove the old row and we have the line pointer redirection, but we don't have to update any index. So we don't generate wall, we don't update indexes, we are just updating this single page. So for a table with 10 indexes or 100 indexes, we only write to a single page. And the index is always valid. So hot updates are crazy efficient, but what is the optimal fill factor? Well, how much space do we need to accommodate hot updates? Well, basically, we only need the space for a single additional row, because if we can update one row, well, we can do a hot update if the space is available on this page. Missing an update within a page is a pity. Missing a hot update can be much more painful, especially when you have a lot of indexes. But there's a complication. You can only remove old versions of row and when the multi-version concurrency control tells you so. So you can only remove information which is no longer required by any running transaction. And besides, you can also have batch updates. So if you want to do a batch update, you need to have space for all the rows in the batch. So this kind of complicates matters. Well, some final notes. A dead row is not wasted space. A dead row is actually an inefficient index pointer pointing to nowhere. You can have a lot of table bloat without a single dead row. Imagine we have this table and the vacuum process just cleaned up the table. That means there are no dead rows, but there's a lot of empty space in all of your pages. So there's no dead rows, but you can have a lot of bloat. And only bloat refers to wasted space within a table or within a page. Well, now back to Dave, how this technical stuff all translates into more day-to-day business.
Okay, thank you very much, Derk, for going through all the core concepts. So the question is now we have some sort of grounding in what the core concepts of what right amplification is. How do we manage things more efficiently, and what do we track and what do we monitor in Postgres? And Yeah, so, and that's where that can be quite tricky because there isn't too much advice out there on the internet at the moment about this. Lorenzo put in this on the Cybertech post on hot updates and right amplifications. He refers to the PG stats user tables, and two of the metrics there are the total number of updates, that's since the Postgres instance started for that table, and the total number of hot updates. So this is a starting point, and it's a very good starting point, but in practice we need quite a lot more than this. So, and we've started using Prometheus and Grafana. So a single point in time check is a good start, but we really need analysis over time. So this shows an incident we had a while back, and you can see that on November 30th, December 1st, December 2nd, December 3rd, it's all lots and lots of green. Those are lots and lots of hot updates. And then after that, we see a tail off, and you see the workload switching into non-hot updates. And these are the sorts of things we can do with Prometheus and Grafana by loading the data. And those are the two metrics which Lorenzo mentioned in his blog post on how to mention this. But we've gone a little bit further. So we're using the default Prometheus Postgres exporter, and we're using the PG stats user tables, which we pull every 5 minutes. We look at the total number of rows, the total number of inserts, the updated rows divided between hot and regular ones, or hot or not, and dead row counts. So those are the four key metrics we've configured or we've focused on. And so this shows you this shows you a use case from Adyen with a monthly partition table, and you can see on the first day of the month, and this is from January, you can see the yellow line shows the inserts, which start off quite high at close to 1 million. And then you can see that in each time interval, I think they're 5-minute time intervals, they drop off quite quickly. Whereas on the blue side, you can see they actually start off very low, but they steadily creep. And by the end of the day, the blue updates are completely dominating the inserts. So this is starting to look like an update heavy workload. And if we extend this graph to the first week, you can see that trend only continues. So if you follow the blue line, it's way higher than the yellow line. There are 0 deletes. We also track those. But this is a classic sort of scenario where you've got an update heavy workload for this table. Okay, so one of the things we know that for the processing, we know that the updates were also potentially, they weren't the columns being updated. It wasn't an extreme table. 15 columns and 6 indexes, something of that order. It was a pretty normal table. But the columns being updated were not indexed, so it should be able to do hot updates. But the problem was we had 100% fill factor in January. Now we reran in February, the next month. At the beginning of the month, we after the table was created, we set an 85% fill factor. And you can see the difference very dramatically by tracking dead rows. So in January, you get these very sharp spikes upwards. It drops back to 0. When it drops back to 0, very suddenly, that's the vacuum operation completing. The metric goes from, so it goes up at one point, it goes from 70 million to 0. Now, that goes on throughout January, whereas if you look at February, it starts off pretty flat. And by scale, the numbers are just way smaller. There's a few vacuum operations until you get to February the 6th, where something awkward happens. It's nothing like as bad as it was before, but it's obviously there's a bit of a glitch on February the 6th. The bottom graph for February goes on a scale of 0 to 40 million, whereas the top graph in January goes from 0 to 70 million. So the bottom graph is I squashed them up a little bit, so 0 to 40 to 0 to 70. So it's really, February was dramatically better, and we were delighted when we saw these metrics. But we still want to understand what happened on February the 6th, and we're going to come on to that in a little bit. So yeah, February the 6th, there's a blip. Right. So before, also I want to mention two other metrics we're using, which gained from the Prometheus exporter. So we're looking at the table and index size and the wall generation, which is set at the cluster level. So we can't see the wall for a table. We see that for the whole cluster, but it's still interesting to review. So this is the wall generation, the rolling wall generation for the cluster. So this is all tables, all work. And you can see that in January with 100% fill factor for this very key table for this, for this whole cluster, this whole instance, you can see it was averaging around 1.1 terabytes every 8 hours. And then by February, that number has dropped to roughly 0.9. So it's just under a 20% saving. And these are big numbers. This is, this is every 8 hours. So this is a huge amount of wall which is being generated. So that was also very encouraging to see. So saving a lot of disk space and on wall generation on the primary, which has to be shipped to the replicas. So that's network transfer. And then we have to back up these walls. So this is an awful lot of actual work. So that was quite nice to see. And then one of the potential downsides of running with a lower fill factor is that you start off with with more blocks in your table. So if you were to rush in and you had an insert heavy workload and you weren't doing any updates, using the default of 100 would work well. And if you reduced it to 50%, which would be a very extreme case, you would end up doubling your storage. Now, in our case, and this was a very nice surprise, in February, after 1 week, we had 28 terabytes of storage of table plus indexes, in January, whereas in February, with the smaller fill factor, we thought the table indexes might be bigger, but in fact, the total was smaller. And the reason for that is the indexes and the table actually are there's much less dirty rows and much less bloat. So the fact that we're actually putting 15% aside, and trying to leave when we create blocks, we try to create them at 15% empty for future updates, means that actually it was better managed. We actually ended up using less disk and less index. So that was a nice surprise. And if you choose where to set a lower fill factor, you will actually save on table and index size. But that is one area, by default, intuitively, the reason Postgres has the 100% fill factor is for insert heavy workloads, it would be better. Okay, so, yeah. Okay, we'll come back to the questions a little bit. So the long-running queries. So I want to talk a little bit about long-running queries. This was some feedback, some really great feedback we got since the February presentation. So one of the most important lessons learned was long-running queries, massive impact on DB performance. Now that isn't my words, that's not Derk's words, that's from one of the dev teams who are coming back, and they've been tuning their work since the last presentation. So that was really, really, that was music to mine and Derk's ears. We were extremely pleased when we were hearing that sort of feedback. So let's first of all, I'm just going to loop back before we go into the other case, which is pretty exciting for us. Let's just go back to what we did in January and February. And then we have so what happened on February the 6th? Why did the 85% fill factor, why did it stop working so well? Well, what we believe is that there are some very long-running queries, very long-running transactions, possibly on other tables, but somewhere in that database. And therefore, that other transaction could potentially want to see an old row version of this table. And Postgres will delay the single-page cleanup. We'll still use the single-page cleanup, but it will hold on. And then if it holds on too long for doing the single-page cleanup, the 15% free space we have in each block will get saturated. And we have another graph coming up in a little bit which shows that effect very, very neatly. It bounces back quite quickly, but there for about 11 hours it was operating in a very inefficient way, and that's because we believe that there are too many long-running transactions and we want to start breaking them down. So that's what we think happened on February the 6th. Let's just step forward and I want to talk about faster jobs. So we did the presentation just over 2 months ago, and we were immediately afterwards, literally the same day, we were asked to review a process which typically ran slowly after large batch inserts. Now, when a developer comes to you with that sort of statement, what they've actually done is they've been looking and been trying to tune this job for a very long time. It's an important job to them, and they couldn't work out whether it was CPU or I/O or too many updates or other operations causing blocking locks, and they literally hadn't got a good reason about why this job runs slowly. The only thing they'd noticed was that after large batches of inserts, the job seemed to slow down, and they had no reason for it. But after the presentation in February, they think, is this right amplifications, and can we tune it through Fillfactor by tuning the Fillfactor, which was 100%. So we dropped the Fillfactor to 85%, and we almost immediately got a 30% saving in the timing. So here we're looking at the performance of the overall job, and it went from 100% to 30% to 70%, so a 30% saving. So that was pretty simple. That was pretty nice just by simply reducing the Fillfactor. But it gets even better. So the job's running better, significantly better, but it's still taking a long time. They're starting to look at the dashboards and the metrics, and they're looking also, noticing sometimes it runs slow and sometimes it's better. And they see the correlation with long-running queries, long-running transactions, and they've refactored this logic. And now their job has gone from 100% to 70% to 25%. So it's 4x faster. So this is like awesome. We're super pleased that like this is, the devs have reached out to us and we've helped them by tuning a parameter, and then they've gone away and refactored their workload so it works much better with Postgres because they have this heavy update workload on this specific table. So that was really, that was a real high point for me and for Derk, and when we got that feedback. So very exciting. I want to talk, we've lost the title. I did have a title here which said rates of change. Thank you. So if we have a look at the rates of change, so I'll just go back to the raw Postgres export, the raw Postgres metrics. So here, this is just the raw metrics from the Prometheus exporter. And it's just the ones originally we were told in the Cybertech blog post, go away, have a look at your total number of updates and look at how many of them are hot. And you can see in January, the total number of updates goes up to 1 million. Was it 1 billion? It's 1 billion. It goes up to 1 billion by the end of the first week, of which about 2/3 of them are hot updates. That's the green line below. And you can see on the first day or two, the green line is almost flat. And that's because you've inserted a whole bunch of rows, 100% full. And so Postgres has to move those to new blocks. It could have done them as hot, and this is the painful bit, as you could have done them as hot, but we didn't have spare space. And then as spare space starts appearing in old blocks, Postgres does this balancing act and it starts doing more and more hot updates, but it's still inserting rows, and we never really get above 65% by the end of the month. By the end of the week, we got to 60% starting off at 0. Whereas if you look at the chart for February, the green line and the yellow line are tracking very nicely. There is a little bit of drift, particularly around February the 6th, but doesn't appear too bad. So that's a very nice, and this is the raw Postgres metrics, and we're just tracking them over time. Now the next slide. What we did is we're looking at this is similar, and we're just looking at the percentage of hot updates. And that makes it a little bit easier to see. So you can see if you look at January, it starts off at 0, and then first couple of days it's going between 10 and 20, 30%. And it slowly creeps up to sort of 40, 50, 60%. Whereas in February, there was a minor glitch. I mentioned that we didn't immediately set the Fillfactor. So there was 1 million rows which actually are set with the 100% Fillfactor. For this table, that isn't an extreme number, but initially we actually start off with 0. Then we have the Fillfactor at 85. And quite quickly we stabilize at around 90. In fact, just slightly over 90. And if you look very carefully at this graph, you will see it slightly drifting down towards the bottom. So I think it's sort of after February the 6th, you can see it slightly drifting down, and that links in with the high dead rows. And also that brings me on to the next graph. So here, this is the same metric, but instead of looking looking at the total counter, we're just looking at the 8-hour delta. So we're looking at the number of updates we ran in the last 8 hours, and we're looking at how many of them were hot. So here you can see in January, it starts off pretty low, and then instead of what it does, because before it sort of drifts up to 60%, but you can actually see over time it's fluctuating between 80 and 40, which means you are getting quite variable performance. Now in February, you see initially we have a little bit of, we did actually create some rows with 100%, but that was only a very small proportion, but it was right at the beginning, which is why we started off with 0. That's now all been fully automated. So now we start off with the 85% in March, but I wanted to do January to February because they were the closest months before we made this significant change. But here you can see it's running at around about 90% all the time until you get to February the 6th. And there you get this problem, which is, and it falls off, and it starts falling off around midnight, and it drops very, very sharply until it gets to only 20% hot updates by 11, and then it bounces back. Now, this is what we believe, that there's a long-running transaction. It will have started shortly before midnight, maybe an hour or two, and then at that point, we start using up that 15% contingency we have in every block. And then it starts disappearing. You can see that accelerates a little bit, the drop. And then around about 11 o'clock, it bounces back quite sharply. And that's when and the nice thing there is as soon as the long-running transaction finishes, there's just an enormous amount of single-page cleanups which can run almost immediately. So it recovers relatively quickly, but I would be much happier if we didn't have that V trough, because it would make everything run more smoothly. So that's something we know exactly where to look at. We can spot these sorts of patterns through this graph. And I think that's even more elegant than the dead row one. But there's various ways of looking at these metrics. So these are all on our new hot update and Fillfactor dashboard. Right, so pros and cons, setting expectations. This is what we said in sort of just over 2 months ago. Pros, less dead rows, less bloat, faster updates, particularly for heavy index tables, less wall. The negative impacts was, it could have a negative impact on read performance. The default 100% Fillfactor works really well for the insert-only workload. Think Instagram. One of the cons is this is quite complex for the DBAs. It's a lot of fun for me and Derk to tinker around at low-level metrics, but it's a lot of work, and it'd probably be better if we were doing something else for Adyen. But it's important that we do dive it deep here, because it's so important for when you're to be aware of this. Adyen's a company which is using Postgres very heavily, and generally it works really, really well. But they have got this one gotcha, which is affecting a few tables. The other disadvantage, of course, that all the devs need to be aware of this, particularly if you're adding indexes or extra columns to an update statement. If you change the where clause to an update statement, that isn't so much of an issue. It's when you add an extra column. That column is indexed, that would block a hot update. And then point C, I've added that this morning. That was one thing we didn't have mentioned on this slide, but the long-running queries, because we're seeing that becoming more and more important. Any long-running transaction in the database will can end up blocking hot updates, because we've used up our reserve over 5, 6, 10 hours. So we need to be really careful and really tight for that. Okay, so that was the expectations we set 2 months ago when we first started off on this path. And then actual achievements, it's actually been much better than we'd hoped. We've got faster updates, less vacuum work, which is saving a lot on I/O and CPU. It's also generating a lot less wall. which is also saving on network load and backups. We had a surprise bonus that we actually start, if you do this on the right tables, you end up with smaller tables, particularly on the index size. So if you think of the aggregate for the table, which is a table and its associated indexes, typically you've got a table that say has 5 or 6 indexes. We're saving this space overall there. The indexes are also more efficient and less bloat, at least faster reads, everything's tighter. So we're also seeing faster jobs and generally Postgres scales better. The cons, we haven't really hit any except for, this does require a lot of tuning work for DBAs and devs. So quite a lot of that is a significant con. But in terms of raw hardware and processing and throughput, it's all been win-win-win. So that's really very encouraging. So we've got one last topic, 5 key slides for Postgres devs to remember, and this is exactly the same as before. Okay, so when creating a new index, if the index involves a column which is frequently updated on a hot update, performance will fall off a cliff. So if you're adding an index to a regular, which around a regular update, it would just steadily go down. But in Postgres, if it's a hot update, performance would really fall off a cliff, and it could be really quite painful. So be very careful when adding indexes. Similarly, if you change a very frequently run update statement, you add a column. It's possible that a whole update statement could switch from hot to regular, and again, performance would fall off a cliff. DBAs often get asked to review indexes. DBAs are not often asked to review update statements, including column lists. But in Postgres, if it's a very frequently run update statement, that is something to bear in mind. Long-running queries, they can confound database performance over time, particularly because of the Postgres problems with these very frequently updated tables. So really keep an eye out for long-running queries. It can cause write amplification problems as well. We're encouraging the devs to think about smaller batches, which I think some of the successes which the one team we mentioned earlier have had in their work for the last couple of months. And the last one is be extra careful when working with heavily updated tables. And the Prometheus metrics will show you if your table is heavily updated. And we saw those numbers going up into the billions of updates over a week. That only went up over the month. So those are the 5 key points for our devs to remember. That's the end of